did that disappear? You're going to freeze up on me now. There we go. First time I ever did that. Da-da-da-da-da-da. Okay, right there. Beautiful. Okay, so what we want to talk about now is the relationship between the Ka of a weak acid and then the Kb of its conjugate base. And I will show you the relationship here with the example using HF as my weak acid, and then obviously F minus as the conjugate base. Eventually, I'm going to ask you to take a look at your Ka-Kb data sheet to check the relationship. So if you have that thing nearby, that would be great. And all I'm asking for in this space here is the equilibrium expression, and I'm going to fill that in a moment. And again, if you're at this spot, you could easily do it. H3O plus times F minus over HF. Actually, I can substitute that in there. So all I'm asking for in this case is, what is that equilibrium expression? Remember, it's products over reactants. And, oh, excellent. Yeah, the smart notebook hasn't even started. That's good, which means I can't write. This is just getting great. Good stuff. Let's freeze that. See if I can fix that as you guys are writing. Okay, now I have the ability to write again on the screen. Excellent. So all I'm looking for here in this case is just to, I guess, remind ourselves, right? Products, we're not including the liquids. So concentration of H3O plus times the concentration of F minus over the concentration of HF, all right? And we don't include the water, right? So now if I'm looking at the conjugate base, behaving as a base, all right? Because up to this point, we know how to deal with weak acids. We've got that nice shortcut equation, the H3O plus square root of Ka times the initial concentration of the weak acid. And we also know how to deal with a base, OH minus is equal to the square root of the Kb times the concentration of the initial base. But what I want to talk about now is the conjugate base versus the acid, or the conjugate acid versus the base. And I want to talk about the relationship between these two. So if we then have F minus, let's say we've got F minus in some water instead of some HF. Well, it is a conjugate base of HF, and because it's a conjugate base, it's going to behave as a base, and it is therefore going to react with water and produce some OH. It is a conjugate base. So if we write down then the relationship for this, HF times OH minus over the F minus, all right? And so now I'm asking you, in order to see the relationship, multiply these two expressions together, all right? Now I'm wondering if I can do this right on the side of this slide. I don't know if I have enough room, but I think I do. If I were to do Ka of the acid times Kb of its own conjugate base, I would get a relationship that looks like this. H3O plus, I'm just rewriting F minus over HF, and then I'm going to have HF OH minus over, I'm on the bottom one here, F minus. What can I do with that expression? Yep. Yeah. So HFs are gone, F minuses are gone, and therefore I have H3O plus times the OH. And we've already encountered this. This is that K for a very special relationship. We call that Kw. I don't know if you remember that, but that's that water ionization constant, which determines the concentration of the H3O plus and the OH minus. So this is equal to Kw, all right? And that's very important. In the end, and again, I don't think I have a slide. Maybe I do have a space to write something down here. Let me see if I've got it next. I'll write it at the top here. I'll bring it back. Everybody you get down what you need to get down here, and then I'm going to just summarize on the top of the next slide there. So when we multiply Ka times Kb, we get H3O plus times OH, which is the Kw. So what that essentially means is, it means that need some pen here. Kw is also equal to Ka times Kb for an acid and its conjugate base, or a base and its conjugate acid. Which means if you know one, you can always get the K for the other. Now, I give you a table that contains Kas and Kbs. And I don't know if you noticed, across horizontally on that table is the conjugate base. So take a look at the Ka of whichever acid you'd like. Acetic acid. I think it's 1.8 times 10 to the minus 5 or something. We've used it a fair bit. It really makes no difference which you choose, but get your calculators out and take the number that's on the left for the acid and multiply it by the number that's on the right. And what do you get? Yeah, Christian? Excellent. Pick any other pair. Do it again. I'm hoping you're noticing a trend. So it's going to get 1 times 10 to the negative 14. And that's what the Kw is, 1.0 times 10 to the negative 14. Remember, that defines our pH scale. It defines the value of the H3O plus, et cetera, et cetera. Now, I give you the table for the test. But let's say I give you something that isn't on that table, and I ask you to find the Ka or the Kb. You simply use this relationship to find that. So I know that F minus is on there, and you could probably just check, what the F minus value is. But the purpose of these examples is to go through the motions and determine what the other value is. So if I have Kw equals Ka times Kb, and I want to determine the value of Kb, then Kb is going to be equal to Kw over the Ka, because I just brought that Ka to the other side, and that's equal to 1.0 times 10 to the minus 14 over 6.6 times 10 to the minus 4, and that will get us then the Kb for F minus. All right? So there is a very simple relationship that relates the Ka of one acid with its conjugate base Kb, or vice versa. If I have a base, I could get the relationship for the acid. It's looking like we're 10 to the minus 10 range, right? Because 10 to the minus 14 divided by 10 to the minus 4. What do you got there, Ryan? 1.5 times 10 to the negative 11. And if you check your sheet, I'm pretty sure HF is on there. You could probably check that out, make sure it's correct, et cetera, et cetera. But still, it's important to know that relationship. On a test, I could give you one that isn't on that page, ask you to figure it out. It's an important little relationship. Yeah, don't mind that. It just says if we know the Ka for an acid, we can determine the Kb for the conjugate base and vice versa. And here's just one more, and then there are some practice problems. But I'm not going to let you work because I want to talk about this relationship a little bit in more detail, and I want to draw a little graphic to represent this relationship because it's going to become important in our next lesson where we analyze acid-base properties of salts. We have to start really thinking about how that conjugate base behaves. So this is just the opposite here. We've got a base, pyridine. We know the Kb is that value. Determine the Ka. And so in this case, Ka is the Kw divided by the Kb that we know. And this is what, 1.5 times 10 to the minus 9. And what do we get there? The Ka is looking like times 10 to the minus, goodness gracious, 5 maybe, somewhere around there. What do you got? 6.7 times 10 to the negative 6. Any questions or concerns on that relationship? Mathematically, it's very simple. But what I want to talk about now is in terms of their strengths, because what we need to talk about next is comparing different acids and bases and conjugate acids and conjugate bases, and we need to compare them and discuss which is stronger. We need to talk in terms of their strengths. We have an idea on what a strong acid is. All the H's fall off. And we have an idea on what a weak acid is. Not all of the H's fall off, but we really need to be able to compare them critically so that we can make sense on which one is stronger, right? If we're comparing two weak acids, the question becomes which one is stronger, all right? So there is a little bit of homework out of the book here on this. Let's see, what is this? Oh, I don't want to do this. I don't want to do this calculation because I want to get to the rest. But the practice problems that you're going to be given will also have some straightforward weak acid, weak base problems. And what we're saying now is, if we know that the acetate ion is what we're dealing with, all right, the acetate ion, go find that on your page. Actually, you know what? We better do this problem. We better do this problem. It is an important idea. It's a good little review as well. So now what we've done so far in this unit, yeah, we've talked about strong acids, we've talked about pH, pOH, all that stuff. Put that aside. Essentially new, we've learned two things. We've learned that if we have a weak acid and the approximation is true, we can determine the concentration of the H3O plus by taking the square root of the Ka times the HA initial, right? And we did weak acid problems, right? This is our weak acid equation. I'm doing a little kind of summary of what we did last week here right under this question, which is fine. I'm not necessarily using that equation. I'm just saying remember, because it's Monday and I can tell we're all kind of groggy a little bit. We also learned that if we're dealing with a weak base and the approximation is true, then I can take the Kb and I can multiply that by the B, the concentration of the base initial, and I'm going to solve that problem using the weak base equation. All right? If the approximation is true. So now we've talked about the fact that there's a relationship between the Ka and Kb of an acid and its conjugate base, or vice versa, which means now the water becomes a little muddy. If I throw a question at you like that one right there, determine the pH of 0.2 moles per liter of a solution that contains the acetate ion, not acetic acid, but the acetate ion, you have to decide whether we're talking about a weak acid or a weak base situation. So you need to decide whether I'm going to use the first equation or the second equation. Because now it's not nice and neat. Now it's not, oh, by the way, this is a weak acid problem. Oh, and this is a weak base problem. It could be, this is a conjugate acid problem or a conjugate base problem. The nice thing is it doesn't matter whether it's a weak base or whether it's a conjugate base. You treat it the same way. It's still a base. So now we need to really ask ourselves, what's in the water? We've dumped some acetate ion into some water, and the question is, am I treating this like a weak acid, or am I treating this like a weak base? What's the answer? What are we treating this question as? And this is imperative, because from here on to the end of the week, we're going to be throwing you all kinds of different ions, or maybe even molecules, and you've got to know whether I'm dealing with a weak acid or a weak base. That's what it comes down to. What is the acetate ion? paramount. Absolutely paramount. We've got to have it. I'm looking to pick on some people. I'm going to pick on Jenna. She looked at her page. What do you think that is? What's that going to behave as? Yeah, very good. It is a weak base. How did you know?
5.6 times.
What is it that you looked at? So she went to the page. She found acetate, noticed it was on the right-hand side. Noticed that it had a Kb associated with it. Therefore, it's a weak base. That's good logic. I like that. That's excellent. Technically, it's the conjugate base of what? What's it the conjugate base of? Acetic acid, which is right beside it on the other side. Very good. So this is a weak base. So which of my two equations am I going to use to solve this problem? Jenna? The OH one. So even though acetate comes from acetic acid, it's still a weak base and is going to make the water basic. So this is a weak base, which means I'm going to use OH minus. And you know what? In an ideal world, I give you the Ka and you calculate the Kb from the Ka that I just taught you. But we've got a page that has the Kb straight on it, which is fine. What is the Kb for this? Times 10 to the minus 10. We have the concentration, 0.20. That's going to get me the OH concentration. I can then get the POH, and then I can get the pH. So essentially, what we're saying now is you've got to be very critical about what is in the water. Question? What did I do? 0.020. Thank you. So now we're going to treat those conjugate bases as if they're regular good old bases, and they are. They will make a solution basic. You might as well finish it, Jenna. You've knocked it out the park here. You got a POH? 10.95. 3.05. We like that? We got supporters on that? Okay? So be aware now, you've got to really think critically. Even though acetate comes from an acid, it's a conjugate base, and it will make the solution basic if it is in the water. All right? And I hope that's the last one, because that's what I was thinking that was the last one. Yeah, there's some practice problems. Do you want me to back that up? Did everybody get down what they needed to get? We're good? So there are some practice problems that deal with acids in their conjugate base or bases in their conjugate acids. So again, the equations are pretty straightforward. It's when you use them is the trick, and we'll work on that for the rest of the week. Now I have one more thing that I want to talk about, and I'm going to attempt to do this on the Smart Notebook, and I have no idea how well this is going to work. I'm going to give it my best shot. Questions, concerns, issues? We're good? Okay. So I'm going to attempt to do this on Smart Notebook. Essentially, what I want to do is I want to compare the relative strengths of Kas and Kbs. So I'm going to give this a shot. Relative strengths of Kas and Kbs. All right? And I've essentially got two scales that are supposed to be like a pH scale, but they're not a pH scale. On the top scale, I'm going to write Ka values, which means I'm going to be dealing with acids. And on the bottom scale, I'm going to be putting Kb values, which means I'm going to be dealing with bases. Whether they're conjugate bases or whether they're just regular bases, it doesn't make any difference. I'm going to slide this up just a little bit. That title said Relative Strengths of Kas and Kbs. Now, when I do this on my paper here, and this is the way I've done this in the past, I use a nice ruler because I want, again, 14 units, just like our pH scale, except I'm not going to be putting them in whole numbers. I want here in the middle, where's the black pen? 10 to the negative 7, right? In other words, I'm not putting a power number. I'm not taking the power out of it. I'm just putting the actual value of the Kas. Over here, I'm going to put here 10 to the 0, just like I would if it was kind of like a pH scale, but it's not. And up here, I'm going to put 10 to the negative 14. And I'm going to do the exact same thing down here on the Kb scale. 10 to the negative 7, 10 to the 0, and 10 to the negative 14. Okay? All right? And all I simply want to do is plot on there some acids and their conjugate base, and perhaps a base and its conjugate acid, so that we can talk about their strengths. Now, before I continue, if I'm way down here to 10 to the negative 14, what's the strength of the acid going to be if the Ka value is way over here at 10 to the negative 14? How would you describe that particular acid if it has a K of 10 to the negative 14, Jess? Weak, not just weak, but let's call it super weak. Like, I mean so weak the H's are hardly going to fall off. Does that make sense? So way down here, we're going to have our super weak, okay? And if I have an acid that has a K of 10 to the 0 or 10 to the 1 or 10 to the 6, how would we describe the acids over here? Strong, right? These would be strong. I don't really need to put super strong. Maybe I will, just because super like is a neat word. Super strong. All right, they're strong. They're all going to fall off there. Now, in the middle here, I've got this 10 to the minus 7. We've been calling them weak acids and weak bases. But to just kind of differentiate between the super weak, where an H hardly ever falls off, I'm going to put here in the middle moderately weak. All right? So it's like moderately weak. It's kind of weak. It's weak where we can use the shortcut, but it will still change the pH. These super weak guys, we can use the shortcut, but it really doesn't really change the pH because hardly any H's fall off. Does that make sense? Okay. So let's get some data here. Could somebody find me the Ka for acetic acid? Ka for acetic acid. I want to plot it on my Ka graph. What do you got there, Shauna? So -5. If this is 0, then I'm going like 1, 2, 3, 4, 5, 6, 7. I want to put it right in here. Oops, and I don't want yellow. I want black. I want to put it right in here. And could you tell me the number again? 1 point. So I'm going to put here 1.8 times 10 to the negative 5. And this is acetic acid, CH3COOH. And if we use our Ka-Kb relationship, we could figure out the Kb of the acetate ion, and it's going to be that they multiply to 10 to the negative 14, which means I'm going to have about a 10 to the negative 10 or negative 9. What is the number for acetate right beside it? Christian, what do you got? Now, I'm on the Kb scale, but I'm now 10 to the negative 10, so that's 8, 9, 10. And in reality, I will be exactly the same distance from that negative 7 as I was on the Ka, because that Ka-Kb relationship will always multiply to negative 14, so you automatically flip down to the opposite side. It automatically happens mathematically. So what was the number again, Christian? I was getting the negative part, but negative 10, and that's CH3COO minus. And just to visually represent it, I like to take a ruler. You guys use a ruler, but I'm going to just use a line. When you have a Ka and you find its Kb, it will always cut across that 10 to the negative 7 and will go on the opposite side of 10 to the negative 7. So what happens then? Here then we have a moderately weak acid, and when it loses its H, it becomes a moderately weak base, but it's a little weaker than what the acid was. Does that make sense to everybody? I got a moderately weak acid, slightly stronger than the middle, and when it loses its H, it becomes a base that is still moderately weak, but it is weaker than what the acid was. Acetic acid and its acetate is better at being an acid than it is at being a base. All right? If this is confusing, I'm going to keep talking. We can laugh at the book on the ground. That's great. Let's take a look at now a base. Somebody find me the Kb for NH3, ammonia. What do we got? Yep. Handily, it's the same as the Ka for acetic acid. 1.8 times 10 to the negative 5. That's for NH3. So NH3 is a moderately weak base. It's slightly stronger than that midpoint. So if we then take a look at the Ka of its conjugate acid, because it's the same value, I'm going to have the same on the other side because of that relationship. 5.6 times 10 to the negative 10. And again, that's for NH4 plus. And again, just to visually represent it, we cut across the middle, and our moderately weak base, which is a little bit on the stronger side, becomes an even weaker acid. But still, it's a moderately weak acid that has acidic ability. Okay? Let's now take a look at something like acetic acid. What's the Ka for a strong acid? Sorry, not acetic acid, hydrochloric acid. What's the Ka for a strong acid like hydrochloric acid? What do you got there, Jenna? 1 times 10 to the 6th. That puts me like way out here, right? So I'm going to just put out here 1 times 10 to the 6th HCl, and that is a super strong acid. What's the Kb for Cl minus? We never really think of chloride as being a base, but what's the value? Yep. So where does that put me? Way out here on the backside here. It actually would put me equal distance out this way. Way out the backside. 1.0 times 10 to the negative, don't have enough room here, negative 20. Negative 20. That's for the Cl minus. Cl minus. How would you describe HCl? How would you describe that? Super strong. If we were to look at chloride, just in water, Cl minus, how would you describe that as a base? Super weak. It's so weak it does nothing. Super weak bases sit around in the water and they don't even play the game worth 2 cents. They're terrible at it. We actually have another term for ions that don't want to play the game. Ions that just kind of stand there. All right, chloride, you're in the water. Come on, you can play. You're a base. You're a super weak base, but you could play. No, I don't want to play. What do we call those ions that don't do anything? They come to the party, but they don't play the game. Yep. Observational ions. Yes, observational ions. No, spectator ions. These guys down here are spectators. They're spectator ions. The chloride ion in water technically is a super weak base, but it's so weak it doesn't do anything. It doesn't play the game. Let's take a look finally at a base equivalent. Now on that table, there is no strong bases. So let's just pick one. We know a strong base. NaOH is a strong base. I have no idea what the Kb value is, but let's say it's really big. Good enough. It's going to be a huge number. All the OHs fall off, which means we can think of when the OH falls off, the Na, we can think of the Na plus as if it's some kind of a conjugate acid. And it technically is. Where would it be? Way out here. So if I then had Na plus as a conjugate acid, what would the size of its Ka value be? Yep. Very small, super small. And we already know this. Sodium in the water, which is technically the conjugate base of a the conjugate acid of a super strong base, they're going to go overtime, folks, I guarantee it, in that assembly. So I'm going to finish this off. So I know you're getting a little excited, but I'm guaranteed they're going to go a little overtime. So Na plus, I want you now to think of Na plus as if it came from from NaOH, which is a super strong base. That automatically makes Na a super weak conjugate acid. And if it's super weak, what do we call it? It's not doing anything. It's not playing the game. Yep. It's a spectator as well. Spectator. All right? And again, just to finish off this illustration, going from that super strong, it cuts all the way across to become super weak. It's conjugate, whatever it is. And same thing here with the base. It goes from super strong to becoming super weak. And if I did my picture properly, all of these things should be crossing in the middle because of that relationship between Ka and Kb. Because tomorrow we're going to have to critically be looking at ions, and we're going to have to ask ourselves the question, what is this thing going to behave as? Is it going to behave as a moderately weak acid or a moderately weak base? Or is the ion going to behave as like a super weak acid, a spectator, or a super weak base? We won't be dealing with the super strong guys. That was just to illustrate the ions. And that hopefully helps you, guide you into answering the questions. What's in the water? Is it an acid in the water? Is there a base in the water? Do I have to use an acid equation or a base equation? Because that's what it's going to come down to. Okay, now I'm finished. I'm not guaranteeing, but I'm thinking they're likely going to go another 10 minutes. But you guys are big people. You can work on whatever you feel you need to work on. Yep. There you go.